Hi, I'm Alexandra Nozika, and today I want to tell you about the project we've been doing for JetBrains Research collaboration for the last year. Currently, this project is called VisionForge, and it is actually a visualization platform based on the DataForge framework we've been doing last several years. And currently it's focused on the 3D visualization for particle physics. Let's start from the beginning, from the motivation. Probably you all saw pictures like that when you have some kind of great announcement from the collider, from LHC at CERN or other accelerator, when you have a lot of tracks, a lot of particle hits, and you can't understand a thing, but physicists probably could understand something from this picture. Actually, we really need those pictures to understand what happens in each specific event, but as you probably can see, we need a lot of three-dimensional visualization to make it work. This particular is news from CERN, recent news actually. So now let's see what we can do to make it work. We need some kind of visualization platform, and we need some kind of user API to make it work, to make it available to physicists. And even if we have a lot of software for graphics, for 3D graphics, for games, etc., most of it is not easy to access. You have to have specific knowledge in order to make it happen, and for each and every experiment you need to create it from the scratch, which requires a lot of money, a lot of time, and that's why we decided that we need something new, something easily accessible, and we are doing it using Kotlin Multiplatform technology. Now let me show you some demonstration. For example, here you see this visualization in a browser, and we have some primitives like like shapes, three-dimensional shapes, and we have dynamic change of properties, which is not available on most of scientific visualization tools. And we have custom rotations, custom figures like this tube, and we can change the scale, and even tools for making tracks and other things, and even labels. Here we can place labels on the boxes. It's very powerful technology, you probably know. Also there is composite solid geometry operations like these ones, and this one is also a CCG with manually created objects. Now let me show you an actual physics demonstration. Here on this picture you see an event in an accelerator, and but not only accelerator requires this kind of framework, they are also needed for non-accelerator physics. For example, here you can see actual model of deep underground muon monitor experiment, which was performed in the Canfranc laboratory in Spain. And this is actually a working model. It allows us to see this model, and you see each one of those pixels is actually a detector, and we can see there are 3 layers of those detectors, and actual scale like meter over meter here, and we can see those layers, those detectors layers, and the top layer we can select it, and the bottom layer and middle layer, and also we have this group for tracks, and the tracks, we can actually see the tracks. Let's click here, and here is the muon. Here you see that it hit the top layer, one detector in the top layer, one detector in the middle layer, and the 2 detectors in the bottom layer, because we can enlarge it and see that it passed through both detectors. It's actually quite a frequent event, and this is exactly why we need visualization tools. For example, we don't need the top layer here, and we make it invisible. Yeah, now I can see how this event passed here, and then we make it visible again, or we can make it wireframe, so transparent, and we can see the event here. Okay. What is important is that this application is actually a full stack application. You see here this next button, and it generates new events, and there is actual physics simulation running on the backend here, and it's this application communicates with the backend. It's a rather simplified simulation. The more complex simulation was used in the real experiment, and a recent article is based on it. But in this case, we run a slightly simplified simulation, and it's run on the backend, and it sends the data to the front end to be visualized here, and we can clear, and it's clear again. Now let me go to the final, and we actually can export the data. We can export the data from this visualization. We can place settings and export. And yes, we now have a JSON object encompassing all the data that including the changes we've made. For example, we can change colors like this, and whenever I go here and change the color, now it's red. Actually, this framework has a very complicated inner structure. For example, there are those objects and groups, and each object could have a style, and each object could have a prototype, so several objects with the same shape share the same geometry, and it saves a lot of time in rendering and a lot of place in this output object. Now, for the last example, let us see actual detector, actual accelerator experiment. Here we have a not fully correct model of BM and at an experiment at Nika Collider at Dubna. It's not quite accurate, but most of the things are here because we have outdated geometry file here. Now you can see those green things are magnets, and it's where actual we detect how the particle go in this magnet, and we can see different types of magnets, and we can enlarge and see that those detectors here are pretty complicated, a lot of different things and different detectors, and we can also turn some things off in order to make it more visible. And here we have a lot of pixel detectors, so called colorimeters. Original geometry consists of about 400,000 of objects. Of course, it requires a lot of optimization to make all those objects observable and interactable, which is more important. And here, this is the place there a beam goes in. It's a hole in the detector here. Yes, we can hear it. So it's here. Now we can also show access, and we can export this the model, and we can dynamically load new models here. If we want, for example, I can reload this page, and it will by default load the more simple model with different rotations and different other things that it's invisible. And we can even change the default rotation order of elements with the same angles. Now, going back to Kotlin, I probably won't show you a lot of code right now, but what is important in this project is that it's a complete Kotlin multi-platform, and it's the most part is done in Kotlin for JavaScript compiler, which probably it is not the project of this scale is not possible to make in such time with the other tools. For example, there are similar software made in CERN, but it took them about 5 years or even 7 years to make it work. In our case, we've done it in about half a year, and it's the rendering mechanics is based on the 3JS library. You probably know about it. Okay, just 3JS. Yes, it's a well-known library for web-based game development and other things, but of course it's a JavaScript library. So in Kotlin we are using the Roper. Originally it was made by Lars Ivar Hatteldal. Sorry if I pronounce it, if my pronunciation is not correct, but the original bindings were done by him, and then we forked it and updated. Sadly, the original bindings are no longer maintained, but we managed to use it anyway. So what is really important about Kotlin for JavaScript? You can probably see here the schemes of the object hierarchy and solid hierarchy, and it's very hard to do without strongly typed language and without tooling to make everything work. And Kotlin actually gives us the tools to make it work, to debug errors, and to publish the project very soon, and even more important, to make it modular. We can add new modules here with the new geometries, and we plan to add the flat two-dimensional visualization and other tools to this framework. And we can see here, probably we can go to this solid geometry package module, and we can see that there are common module here, which is not very it contains a geometry definition. There is a JavaScript module here which contains the bindings for the 3JS, and also some specific tools to integrate it with our framework. And actually we do have JavaFX based renderer, so these pictures could be made not only in browser but on the desktop using JavaFX three-dimensional renderer. It's not completely ready yet, but we also have it, and it helps us a lot with debugging models and finding problems, and one day we definitely will have a fully functional JavaFX based renderer for our geometries as well. Well, this is probably all I wanted to say today. I also wanted to say thanks to Kotlin JS team and of course other Kotlin teams, but all Kotlin JS specifically, because they helped a lot, consulted us a lot on this project, and I hope this platform will prosper and go bigger, better, and will help us make better visualization tools and better tools for science, and not only for science.